So you see problem 5.2 on your screen now. This problem deals with a first order differential equation of this form, where a and b are given here, and note that if a is positive, which it is, the system is stable. Now the goal is to find a control input u that minimizes this finite horizon cost with rho as the tuning knob or the tuning parameter, as well as s, of course. So s captures the cost on the final state w or omega at time t, and rho captures the cost of control. Now we're supposed to use equation 5.7, which is given here. Now before we just use this equation, let's quickly also remember what this equation is all about. So ideally, for solving this NQR finite horizon optimal control problem, we would have to solve the Riccati differential equation. But we saw that there is an alternative, easier method to sort of replace or to avoid solving the Riccati differential equation, and that is by writing down the Hamiltonian system. So the Hamiltonian system is given by this expression, and the boundary conditions for the Hamiltonian system. So now, because we are scalar, I don't need to write down the identity, I can just write 1, because the dimensions of the state and the input here are 1. So for our problem, the Hamiltonian system would look like this. Now, the idea was to, and also the boundary condition. So the idea was to solve this system of linear differential equations with a given boundary condition in closed form, and write down the solution x of t and lambda of t as a function of lambda at time t, and then obtain p of t as lambda of t divided by x of t. So that was the idea, and that led to the derivation of 5.7. So I'll quickly recap what the terms in 5.7 are. So the u corresponds to the eigenvectors of the Hamiltonian matrix. So let's call this matrix H, then H can be decomposed in this form, where U is given by these subblocks U11, U12, U21, U22, and because we are dealing with dimension 1 here, all these are scalars. So these are the U's. The lambda S and the lambda U correspond to the diagonal matrices with stable and unstable eigenvalues. But now again, because we have dimension 1 here, lambda S would be a single eigenvalue that is negative, and lambda U would be a single eigenvalue that's positive or unstable. G So G is another function depending on the U and S, and you can check that expression in the lecture notes. So this is what you want to evaluate. So what you do is, in Matlab, you first do the eigenvalue decomposition of H and get the eigenvectors U, then build P of T given by 5.7, and then have the optimal control input U of T as minus R inverse, which is here 1 over rho, suppose, which is just P of T times X of T. So this is sort of the steps that you need to follow in order to solve the above finite horizon optimal control problem. And this is done in the Matlab files provided to you. Now let's look at a few results. You see here the plot of the gain f of t. So f of t is minus 1 over rho p of t, and the plot shows for different values of rho and s. So this is for rho 10 to the 4, rho 10 to the 3, and this is rho 10 to the 2, all of them with s 0, and this one with rho 10 to the 3 and s some non-zero value. So what you see is that if you increase the rho, you go in this direction, which means the absolute value of the gain decreases. So you go closer to 0 as you increase rho, and that makes sense because increasing rho means you're increasing the cost on the control input. So if you have a higher value of rho, you're saying control is expensive, use less control effort, and that would lead to a smaller value of f of t, which is the gain. So now let's look at the analytical expressions for the gains. So rho in this direction is increasing, which means the control effort, the control cost for B is higher and for C is the highest. So control is the most expensive in C, and you can see that the gain is the lowest for C. You can also see that when the rho value is the lowest, which means that control is cheap, you get the highest gain, Of course, all this is in magnitude, and it drops quite suddenly because of this high value of the exponent to 0, very close to t. Whereas if this exponent is a smaller number, it has to go slowly to t, which means it has to begin earlier and start at a lower value. So now also comparing this one and this one, note that the signs are flipped here, which means that the numerator will not vanish as t goes to 1. Yeah, and so that's it for this problem. Thanks a lot.